Okay, so we went through and solved this the long way, just how I would expect you to solve it at least first. Okay? So we go through, we generate our balanced equation. When we're dealing with our acids and bases, actually not quite yet. Go back to our problem. It tells us that we start with 0.15 molar HNO3. There's our initial concentration. What's our initial concentration of hydrogen ion and nitrate ion? 0. We could go through, solve for Q. Q by definition will be less than K, which means products need to form. We can put in the positive signs there and a negative for our reactant. We can substitute in X. Say X is our concentration of HNO3. What's our concentration of H plus going to increase by? X. How do you know it's just X? The coefficient from the balanced equation. So one nice big advantage of our acid-base chemistry. What are our coefficients going to be in all of our equations? 1. Thankfully, we don't have to worry about our coefficients anymore. Yes? We know it's a negative X because we go back to our initial concentrations and we solve for Q. So it's products over reactants. 0 divided by some number, still going to be 0. So Q is equal to 0. By definition, that's going to be less than K. Yes?
Is it the side where there's a 0, either product or reactant, always has a positive X when it comes to change?
Say that again?
Like the side, either product or reactant, there is a 0 concentration.
Yes.
The change for X is always positive.
Yes. So what we can do is if we're given an equilibrium reaction, wherever we have 0, the reaction is going to have to shift to change that 0 to any number. Okay? So we don't have to calculate Q. We can just look to see where the 0 is. In this case, the 0 is the products. Our products have to increase. Okay? The reason why we didn't do that assumption before or make that statement before as clearly was because what if they weren't all 0? Or we didn't have zeros. So we really do have to go through and solve for Q. It just happens to be when we do have a 0, Q is trivial to solve for. Okay?
What was the algebra step? Can you do that 240 for K? Can you do that in quadratic formula?
I didn't have any space, so I didn't show all that work. So what we would do is first get our equilibrium concentrations. Ice, we'll go back to our ice chart. Initial plus change gives us our equilibrium. So initial plus a negative X is 0.15 minus X. Our equilibrium constant is the concentration of our products over reactants. We could substitute in, we get X squared over 0.15 minus X. Okay? I then jumped immediately to solving for X for a couple reasons. Well, just one. I didn't have any space. Okay? The first thing that we could do is potentially assume that X is really small. So we could plug in X being small and solve for our X squareds. Okay? So we would take our equilibrium constant, 240, times 0.15, square root of that, and we'd get X being a very, very small number. Okay? I think it's really, really small in that case. Well, yeah. No, it's not. Sorry. X is not a really small number. So what we'd have to do is go through and solve the quadratic. You're right. Okay? So that would mean we'd have to 240 times this, get all our coefficients or all our numbers onto one side of the equation, and then solve the quadratic formula for X. Okay? So a lot more work to get that X value. And I just didn't have the space to go through and show that quadratic solve. Okay? Does somebody have the condensed formula so I can put that up here so somebody else wants it? We'd start with X squared, right?
Plus 240x minus 36 equals 0.
If we do negative X squared, we'd have negative 240. Yeah. And then you got negative 36.
Equals 0.
Depending on which side of the equation you put it on. So if you want negative X squared, you can do that. Then it would be negative 240 and positive 36. You just put all your coefficients on one side of the equation versus the other. It's entirely up to you which you want. Okay? You would then go through, solve your quadratic formula for what X is, and you'll get X equaling this number, 0.14991. All that work, and where did I start? Very beginning, I said short way, H plus equals 0.15. Compare that to what our X value was at the end. How the heck did we do that quickly without actually having to do any calculations? And no, it's not just because I know the answer. It's a strong acid. What do strong acids do? Completely dissociate into the ions. If I take one molecule of HNO3, how many molecules of H plus are formed? One. Okay? Based on the balanced equation. So we don't have to solve an ice chart in this case because the definition of a strong anything means it completely dissociates into the ions. We can directly translate the concentration that we started with over into the concentration of our products. Okay? So that's one of the advantages of our strong acids. Okay? We can still go back to the basics and solve the long way. But we end up finding that we get the exact same answer. Okay? You mad that I made you go through and solve it the long way? Okay. The intent is that you discover it on your own and realize that you don't have to do all of that. Yes?
The short way doesn't take into account the concentration that we just found. Like, where do we...
So the short way, what we're saying is because it's a strong acid, when I take HNO3, it completely dissociates into the ions. So if I take one molecule of HNO3, how many atoms of H plus are generated? One. Because it's a strong acid, I know it completely dissociates. So if I start with 0.15 moles of it, of HNO3, how many moles of H plus are generated? 0.15. Okay? Every single time, because it's strong. Okay? Does that make sense? So when you evaluate your strong acid-base problems, you can just immediately translate that information over. The one case where that might get dicey is if we started with a 1 molar solution of calcium hydroxide. What does calcium hydroxide look like? So you guys can all come up with, know your nomenclature perfectly. Upper left-hand corner. Calcium hydroxide. What charge is calcium? +2, which means I need 2 hydroxide. If I start with a 1 molar solution of calcium hydroxide, what is the molarity of hydroxide in that solution? 2 molar because of the coefficients from my formula. Okay? Most of our acid-base equilibria is 1 to 1. When we're looking at our group 2 metals with hydroxide ions, you've got to be a little bit more careful there. Okay? You might see a doubling effect. Okay? Questions about our strong acid? Okay, so what about the other acid, our acetic acid? What's our concentration of H plus there? Do we have a short way? No. How do we solve for the concentration of H plus with our weak acid? We must go through the ice chart, beginning to end. Okay? Should we go through and solve that? No. Good. I like that. Okay, so we won't go through and solve that one. I'll try and come up with the answer later today and post the answer to the announcements so you can match your answer when you go through and solve it and make sure you're getting the same answer. Okay? So we've now brought back the equilibrium constants back into this concept of acids and bases. So what we'll try and do is take advantage of that equilibrium constant and go through a bunch of problems and determine the concentration of H plus. Okay? I did ask that question about hydroxide. We'll come back to that in a second. Okay? If we go through and look at, I think these were the question 3 and 4 when I asked you to go through and look at your acids and bases. We've got acetic acid dissociating in water to give us H plus or H3O plus, an acetate ion. Equation 4, I know there was a typo on the last one. I'm glad no one called me out on it. When we react sodium acetate with water, remember it's aqueous, we definitely dissociate into the ions, but then our acetate ion can react with the water to generate our conjugate acid. and the conjugate base, our hydroxide ion. Okay? What's the relationship between these two equations? Kind of right. They're almost the negative of each other. What happens if we take these two equations and add them together? Close, not quite zero. Do we see HC2, do we see acetic acid show up on the reactant and product side? Yes, it does. Here and here, which means we can cancel those terms. How about sodium acetate? That's a little bit trickier. Kinda no, but kinda yes. Why the kinda yes? What did we say sodium does? Absolutely nothing. So really when we look at sodium acetate, what are we looking at? Acetate ion. Does acetate ion show up on the reactant and product side? Yes. So we can cancel that term out. Do we see H plus on both sides? No. Do we see hydroxide on both sides? And yes, I am ignoring that sodium ion. Do we see water on both sides? So we add these two up and what do we get? H2O goes to H plus and OH minus. Interesting. When we put weak acids and bases into water, what we're looking at is how those weak acids and bases actually affect the standard equilibrium for water. Okay, so we could go through now and look at an equilibrium expression for water. Okay, and that's what this next slide does. So in the process of monitoring this chemistry, what we need to do is look for the concentrations of these things. So when we looked at our acids, we typically classify acids. Any idea why we classify acids as opposed to bases? When I asked about sticking your finger in a solution of acid, what did you guys say? Ouch, that hurt. When we put it into base, the first response that I actually heard, I don't know if anybody else heard it. What was the first response? Nothing happens. That's not true. Okay, why do you assume nothing happens? Because we've ingrained in your head since you were a little kid, acids are bad. Okay, so you're aware of acids being bad. Why do we not look at bases as much? Because we just don't see them quite as frequently. Okay, we don't work with them on an everyday basis. Okay, as we do with our acids. Okay, so when you hear acids or dangers of solutions, acidity is one of our primary concerns because we see that everywhere. Acidity was a measure of what? H plus. So we can monitor our concentration of our solutions of H plus. Okay, so when we go through and define things, we'll look for what's the concentration of H plus in this particular solution. Okay, so we could go back to our water expression, water dissociating into the ions, and we could go through and look at that and come up with an equilibrium expression. So the equilibrium expression for that would be H plus, concentration of H plus times concentration of OH minus times concentration of water. Okay? Is there anything special about that equation? Whoops, don't do that. I ignored. The water is a liquid, which means its concentration doesn't change. What we can do is then say if that water concentration stays constant, I can transfer it over to the other side of the equation. And instead of looking at the equilibrium constant as that, we typically define it as H plus times OH minus. You'll notice in the process of doing this, we've added an extra little addendum to this. What's that addendum? The W. It says KW, not just K anymore. Why KW? Because it's referring to the equilibrium constant with respect to water. Okay? Why bother to go through all of this? Okay? Well, we can now evaluate, as we already saw, our different acids and bases based on their equilibrium constants. Okay? A lot of those are typically found, or you can typically look up. Okay? The really important ones have already been solved for you. One of the most important equilibrium constants that you'll see will be Kw. Okay? So Kw is your concentration of H plus times OH minus, which happens to equal 1 times 10 to the minus 14. Okay? This is an extremely helpful equation because as long as we're in a water solution, what can we do with this equation? Remember the last problem asked you to solve for the concentration of hydroxide. We didn't have the facilities to be able to solve for the concentration of hydroxide before, but what do we have now? We know the concentration of H plus, and we know we're in a water solution. What does that mean about the Kw? It equals 1 times 10 to the minus 14. Which then means, if I know H plus and I know Kw, what can I solve for? OH minus. Okay? When is this equation true? Because I don't think I added that piece of information there. Nope, I didn't. Nothing about pH yet. When is that equation true? When is the Kw equal to 10 to the minus 14? When we're in water, that's a good call. When is the equilibrium constant a constant? When it's at equilibrium and as long as the temperature stays the same. What happens when we change the temperature to our equilibrium constant? It changes. Okay? Which means this is a valid equation, but only when our temperature happens to be at the value that we calculated. What is that temperature going to be? 273 is not a bad idea. Okay, so our standard for kelvins, except what temperature is that in degrees Celsius? 0. How many of your reactions have you run at 0 degrees Celsius? None. Okay? If you think back to even older days, okay, when they were trying to run a reaction, determine equilibrium constants, were they able to get their reactions to 0 degrees Celsius easily? No. So what's an easier? Room temperature, which is, I'm hearing all sorts of numbers there, 298 Kelvin, I think I heard. I want to say it was 25 degrees Celsius, which is 298. Okay? So this equation is only valid when we hold that temperature. What does that mean as far as temperature changes during exams? You can't use this expression, which means it makes it a very difficult problem to solve, which would mean you'd have to see it not possible to solve as a possible answer. Okay? That being said, that's an awful easy way to just kind of get out of doing the problem. You won't see that, okay? At least not frequently. Okay? You need to be aware of when it's valid, when it works, all of the problems you're working with. If it involves trying to figure out the OH minus from H plus or some balance between these, you can assume that you're at that temperature. Okay? The problem would have to add some extra piece of information otherwise. Okay? So we could go backwards and now solve for the concentration of hydroxide. Anybody want to go through and do that yet? Take that as a no. Okay? One of the big issues with this, the numbers that you're looking at are usually these exponential values. You get 10 to the minus 14, 10 to the minus 7. Okay? So you're going to get these really, really small numbers. Problem with these really small numbers, really easy to make mistakes when entering into the calculator. Okay? So please be careful when you enter your numbers into the calculator. Use parentheses. Make sure you're putting it together as appropriately as you can. Okay? It is easy to do that, or easy to make those mistakes. Okay? So we can now look at a way of trying to change that a little bit. So if we're now going to build up some safety rules, okay? If we're running down the hallway and we see some kid say, hey, watch out for that 0.15 molar H plus solution. It'll burn you. That's a lot of effort. Okay? Or we could switch it up and actually say what it's referring to, which is really the hydrogen ion concentration. We could say, hey, Timmy, watch out for that 0.15 molar solution of a strong acid. It's really dangerous. Again, that's a lot of effort. Okay? So we want to come up with some easy way, like a color system, you know, red, peach, green, all those things. So we can say, oh, what color is dangerous for today? Because everybody deals with colors a lot better than numbers. Okay? So what we end up coming up with, or what everybody else came up with, is a system known as the pH and pOH, or even pK of solutions. Okay? So we can get a relatively quick idea of the potential corrosive or caustic hazards for each of these individual solutions. Okay? So we have to understand what this pH or pOH is coming from. pH is going to be referring to acids or our hydrogen ion concentration. The pOH will be referring to our base solutions or our hydroxide solutions. Okay? So we want to be able to look at those numbers and pull something up really quickly and easily. Did we solve for one? Most solutions get you this 10 to the minus, for an acidic solution, 10 to the minus 3 or 4. Okay? If you tell someone to watch out, that solution is 10 to the minus 3, what are you talking about? Okay? It's not easy to teach someone that, particularly little kids. So what we want to do is come up with a number system that allows us to get rid of that 10 to the minus feature and give us a number that's a lot easier to manage. Okay? What numbers are easier to manage? Usually anywhere between 0 and 10. Why 0 and 10? That's how many fingers we've got. Okay? It turns out our pH scale isn't quite exactly 0 to 10. We're looking usually at 0 to 14 are our standard ranges. Okay, so how do we convert our concentrations into this pH system or this P system? Okay, so we want to be able to go through and say these low and high values are bad and to kind of watch out for this middle area, or the middle area is okay. So when we look at our useful scale, we're running from 0 to 14 on each of these. If we're looking at the pH, which is our standard one to look at, 0 is acidic and 14 is basic. What happens when we shift to the pOH? We swap them. Swap them. Okay. We swap those relationships. So when we're looking at our 0 to 14, this is only standard for a pH system or a pH scale. Okay, why do we pick pH and not pOH? It's again ultimately convention. We decided that acids were more dangerous to start with, okay, or more readily available, so we ran with pH, looking for that acid concentration. Okay, so it's again just a convention. You will be asked to convert and calculate both in pH and pOH scales. You need to make sure you're comfortable with both of those systems and what each of those values mean. So now the question is, how do we solve for these? What was that? Do the negative log. Okay? I went through and changed the formatting on this a little bit. I wrote px. Why not pH? Because pH would only apply to pH. What if I wanted the pOH? Instead of X, I have OH. What if I want the pK? I just put in K. Okay? So if you see P anything, what we're saying is the negative log of whatever that number is, whatever that value is. That's our notation. Okay? In the process of doing this, that converts most of our relationships, most of the concentrations that we would see into this 0 to 14 range. That gives us a little bit more quick interpretive power. We don't have to evaluate that negative exponent, what it means, bigger or smaller. We've already seen how bad I am with that. Okay, so the pH or our px works really well for determining that. Okay, so that's one of the big things that we're kind of adding to this. If I give you the pH of a solution, what am I actually telling you? I'm telling you the concentration of hydrogen ion. With that concentration, you can now relate that back to your equilibrium expressions. Okay? So you've got a bunch of now little extra conversions to slide in and out of your problems. Okay? So we can also go through it and kind of look at it as a love-hate relationship. We could go through with our KW and go through and solve and make it a pH system. So at 0 degrees 25 degrees Celsius. We know the kW is 10 to the minus 14. So what we can do is take the log of both sides. Okay, what happens if we take the log of both sides? Sorry, the negative log of both sides. Whoops. What's the negative log of 10 to the negative 14? 14. Which is nice. We took that number that was 10 to some negative power and put it into a nice easy number to deal with. Okay? As far as the negative log of the quantity, that's the same as saying the negative log of our H plus the negative log of our OH minus. What's the negative log of H plus? Of H plus is the pH. What's the negative log of OH? The POH. Okay? We can now, instead of dealing with those exponents, come up with another expression. pH plus POH equals 14. Okay? That comes in handy because now we can relate these different numbers around each other. So depending on what you're asked to solve for, you may want to shift into your P system. Okay? If you're asked for concentrations of hydroxide, you're probably going to want to deal with your Kw being 10 to the minus 14. If you're asked for pHs or POHs, you will probably want to use this other expression, pH plus POH, okay, to go through and solve these. So depending on what system or what information you're given, you may have to shift between these different conversions. Okay? So when working your problems, make sure you know what the question is asked and answer that question. Okay? Questions about any of this so far? Okay. I know I don't have a whole lot of problems in these slides. That's something I've been meaning to put in. I just haven't had time to do it yet. Okay? 15. We will end with this. Okay, so we went through all this mathematics, discussing that. We're going to go through this kind of explanation on what's going on here. We got the idea of what's going on with our strong. We can even look at our weak acids and bases based on their equilibrium constants. We can look at pHs. We can look at POHs. Okay? But what happens when we look at weak versus weaker? Okay, how would we rank these individual acids or bases away from each other? We could go back to our equilibrium constants. And that's great if and when you have equilibrium constants. What if you don't have those numbers? Trying to be able to solve for whether it's a weak or stronger or weaker acid, we need to be able to look at a formula, at the structure itself, and try and predict something about the chemistry. Okay? So given that, how can we predict it? So what we're going to do is ultimately look at stability, okay? Structure and stability, and try and figure out what can happen with each of these cases. Okay? Always, 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 we're going to try and minimize charge. So when we go through and try and predict something being weak or strong, we want to look at how it reacts in water and what ions are generated in that process. Okay? So if we take a look at, say, two acids, let's pick, we'll call it HX. What happens when it hits water? Dissociates into H plus and X minus. All right, let's pick another example. Let's say instead of starting with HX, we start with HY, but positively charged. What happens when it dissociates in water? Still get H plus. Why do we know we get H plus? So we've got that hydrogen in front of our formula. So there's our H plus. Plus what? There's no OH to even look at here, so you can't do that. The only piece left is Y. What charge is Y? Why is 0? It started positive. The H plus comes off as our positive. What's left behind on the Y? No charge. It's neutral. If we now try and look at these two species based on this idea, which of these two would we expect to be the stronger acid? So what we want to do is evaluate based on minimizing charge. When we add these into the solution, we generate these ions. Which of these has less charge? If we look at H+, those are a wash. Okay, so we can effectively cancel those out. Those are not going to impact our overall discussion because it's the same in both cases. Move to the next one, X minus and Y. Which one has the lower charge? Why does the bottom have less charge? It's neutral. Okay, so it's not a lower number, it's more neutral, closer to 0. This bottom one, HY plus, ends up being the stronger acid because when we add it into water, it generates a less charged species than in the case of HX. Okay? So what we looked at there was the easiest example for this, minimizing the charge. There are 4 other rules that you're going to look at, or we're going to look at on, what is today, Wednesday? Thursday? And then we'll kind of push through maybe the rest of this chapter. I'm not sure exactly how far we'll get. I'll try and build a bunch of problems as well so we can work on some problems tomorrow. Maybe even turn it into a quiz. We'll see what happens, see how far I get. Okay?